For millennia, humanity has gazed at the stars and pondered a profound question: are we alone? The search for life beyond Earth, particularly for planets like our own, has captivated scientists and dreamers alike. This quest is driven by a fundamental human desire to explore, to understand our place in the cosmos, and to seek out potential havens for life as we know it. The discovery of another Earth, a twin planet orbiting a distant star, would be one of the most profound discoveries in human history. The vastness of space is almost incomprehensible. Our galaxy alone, the Milky Way, contains billions of stars, each potentially hosting its own planetary system. Astronomers estimate that there are billions of galaxies in the observable universe. Given this staggering number, it seems statistically improbable that Earth is the only planet where life has taken root. The sheer scale of the universe suggests that there are likely countless worlds out there, some of which may harbor life as we know it, or even life as we don't yet know it. The search for Earth-like planets, also known as exoplanets, has accelerated in recent decades thanks to advances in telescope technology and data analysis. We are now able to detect planets around other stars with increasing precision. These discoveries have revealed a staggering diversity of worlds, from gas giants larger than Jupiter to rocky planets smaller than Mercury. Among them are a growing number of potentially habitable planets, worlds that orbit within their star's habitable zone, the region where temperatures are just right for liquid water to exist on the surface. Not all planets are created equal. For a planet to be considered truly Earth-like and potentially habitable, it must possess a specific set of characteristics. These characteristics are essential for the emergence and sustenance of life as we know it, though it's important to remember that life elsewhere may have evolved under very different conditions. The search for life beyond Earth is not limited to finding exact replicas of our own planet, but it does focus on planets with the highest probability of harboring familiar forms of life. First and foremost, a habitable planet needs liquid water, the universal solvent essential for all known life. Water is a remarkably versatile molecule, capable of dissolving a wide range of substances and facilitating the complex chemical reactions necessary for life. A planet's distance from its star is crucial in determining whether water can exist in liquid form. Too close, and the water vaporizes into steam. Too far, and it freezes into ice. In addition to liquid water, a habitable planet needs an atmosphere to regulate temperature and protect life from harmful radiation. Earth's atmosphere, composed primarily of nitrogen and oxygen, acts as a protective blanket, shielding us from the sun's intense ultraviolet rays. It also traps heat, creating a stable climate that allows for liquid water to exist on the surface. The composition and density of an exoplanet's atmosphere are key factors in determining its habitability. Finally, a habitable planet needs a stable environment over long periods, providing life with the time and stability to evolve and thrive. Earth's relatively stable orbit, its protective magnetic field, and its tectonic activity all contribute to its long-term habitability. These factors help to regulate the planet's climate, recycle nutrients, and prevent catastrophic events that could sterilize the surface. In our search for Earth-like exoplanets, we've identified a number of promising candidates, worlds that possess some or all of the characteristics necessary for habitability. These discoveries have ignited the imaginations of scientists and the public alike, offering tantalizing glimpses of what might be out there. While we have yet to find definitive proof of life beyond Earth, these exoplanets represent our best targets in the search for a second home. One such candidate is Kepler 452b, a planet located about 1,400 light-years from Earth in the constellation Cygnus. Discovered in 2015 by NASA's Kepler Space Telescope, Kepler 452b is about 60% larger than Earth and orbits a Sun-like star within its habitable zone. Scientists estimate that Kepler 452b receives about the same amount of sunlight as Earth, suggesting that it could have liquid water on its surface. Another intriguing candidate is Proxima Centauri b, a planet orbiting Proxima Centauri, the closest star to our Sun. Located just 4.2 light-years away, Proxima Centauri b is at least 1.3 times the mass of Earth and orbits its star every 11.2 days. While Proxima Centauri is a red dwarf star, much cooler and fainter than our Sun, Proxima Centauri b orbits within its star's habitable zone. TRAPPIST-1e, a planet in the TRAPPIST-1 system located about 40 light-years from Earth, is another promising target in the search for life beyond our solar system. TRAPPIST-1 is an ultra-cool red dwarf star orbited by 7 Earth-sized planets, 3 of which, including TRAPPIST-1e, are located within the habitable zone. The TRAPPIST-1 system offers a unique opportunity to study the diversity of planetary systems and the potential for life around other stars. While the discovery of potentially habitable exoplanets is a major step towards finding life beyond Earth, the challenges of reaching these distant worlds are immense. The vast distances between stars pose a significant obstacle to interstellar travel, requiring technological leaps that are currently beyond our reach. The journey to even the closest star system would take thousands of years with our current technology. The primary challenge is the sheer scale of interstellar distances. The Voyager 1 spacecraft, the farthest human-made object from Earth, is traveling at a speed of about 38,000 miles per hour. At this speed, it would take Voyager 1 over 70,000 years to reach Proxima Centauri, the closest star to our Sun. To make interstellar travel feasible, we need to develop propulsion systems that can achieve speeds approaching the speed of light. Another challenge is the energy requirements for interstellar travel. Accelerating a spacecraft to even a fraction of the speed of light would require an enormous amount of energy. Traditional chemical rockets, which rely on the combustion of fuel, are simply not efficient enough for interstellar travel. We need to explore alternative propulsion concepts, such as fusion power or antimatter propulsion, which offer the potential for much higher energy yields. The hazards of interstellar space also pose a significant challenge to interstellar travel. Space is a harsh and unforgiving environment, filled with cosmic radiation, micrometeoroids, and extreme temperatures. Any spacecraft designed for interstellar travel would need to be shielded from these hazards to protect its crew and instruments. Developing effective shielding technologies is crucial for the safety and success of any interstellar mission. Despite the formidable challenges, scientists and engineers are actively exploring a range of technologies that could one day enable interstellar travel. These technologies, while still in their infancy, offer a glimmer of hope that we may one day be able to reach the stars and explore the countless worlds that await us. From advanced propulsion systems to innovative spacecraft designs, the quest for interstellar travel is pushing the boundaries of human ingenuity. One promising area of research is in the field of advanced propulsion. Scientists are investigating a number of concepts, including fusion propulsion, antimatter propulsion, and even warp drives, which could theoretically allow spacecraft to travel faster than the speed of light by distorting spacetime. While these technologies are still in the realm of science fiction, they represent the ultimate goal of interstellar travel, to overcome the limitations of distance and time. Another area of active research is in the development of new spacecraft designs. Traditional spacecraft, with their bulky fuel tanks and complex propulsion systems, are ill-suited for interstellar travel. Scientists are exploring alternative designs, such as solar sails, which are propelled by the pressure of sunlight, and laser-powered sails, which would be propelled by powerful laser beams fired from Earth. These concepts offer the potential for faster and more efficient interstellar travel. In addition to propulsion and spacecraft design, scientists are also working on technologies to protect astronauts from the hazards of interstellar space. One promising approach is the development of advanced shielding materials that can deflect cosmic radiation and micrometeoroids. Another approach is to create artificial gravity environments within spacecraft, which would help to mitigate the negative effects of prolonged weightlessness on the human body. The search for Earth-like planets and the quest for interstellar travel are not merely scientific endeavors. They are profound expressions of humanity's innate curiosity and our desire to explore the unknown. These endeavors have the potential to fundamentally alter our understanding of our place in the cosmos and to redefine our future as a species. The discovery of life beyond Earth would have profound philosophical and cultural implications, forcing us to reconsider our place in the universe. The discovery of another Earth, a planet teeming with life, would be a transformative event in human history. It would demonstrate that we are not alone in the universe and that life is a cosmic phenomenon, not just an earthly one. Such a discovery would have profound implications for our understanding of biology, evolution, and the very nature of life itself. It would also raise profound philosophical questions about the nature of consciousness, the meaning of life, and our place in the grand scheme of things. The quest for interstellar travel, while fraught with challenges, holds the promise of expanding humanity's reach beyond our solar system and into the vastness of interstellar space. The ability to travel to other stars would open up a universe of possibilities, allowing us to explore new worlds, discover new life forms, and perhaps even establish a permanent human presence beyond Earth. It would be the ultimate expression of our pioneering spirit and our desire to push the boundaries of what's possible. The search for Earth-like planets and the development of interstellar travel technologies are investments in our future. They are investments in knowledge, in exploration, and in the long-term survival of our species. By pushing the boundaries of science and technology, we are not only expanding our understanding of the universe, but also creating new possibilities for humanity's future. The discoveries we make and the technologies we develop will shape the destiny of our species for generations to come.